This week we're going to talk about acids and bases, and oxidation reduction. Remember, we talked about redox reactions before. We're going to come back to it. It's kind of important. So, before we go that direction, I want to call your attention to, as a reminder, to concentrations of solution. This will come into play with our discussion on acids and bases. Remember, an index of 37 of formalin or formaldehyde or methanol, however you want to say it, is said to be concentrated, which means we have a lot of formaldehyde in the solution. If no more of that solution will dissolve, then we call that a saturated solution. So if we were to reduce it to 1/10 the concentration, so say an index of 3, we would call that a dilute solution. So the process of dilution is the process of taking the concentration and making it lower, lowering the concentration of your solute. So in other words, if you take 100 milliliters of 10 molar sodium chloride, we take 100 milliliters of that. We've got 10 moles per liter of the sodium chloride. And then we can kind of walk through how this is going to play out. There's a lot easier way to do this than this little verbal way of working through it. And that was what I was talking about at the end of the lecture previously. Remember that M1V1 equals M2V2. So initially, if we take 100 milliliters, which is 0.1 liters of 10 molar, so 10 molar times 0.1 liters is equal to, and we're trying to get, what are we trying to get to? It looks like 1 molar kind of thing. How much volume are we going to need? Well, to solve for this thing, now then, this says that we'll need hold on, let me see. We will end up with, what this is saying is we're looking for this V2, right? It says that V2 will then equal to 1.0 liters. That means we will have 1 liter of our dilute solution. Okay, so that's that M1V1 equals M2V2. I use it this other way down here because you'll see it either direction. C1V1 equals C2V2, where C is your concentration. All right, so this concentration is pretty important. Remember, last time I talked about a couple of things. I talked about hypertonic and hypotonic with response to electrolytes and electrolytic solutions. So we need to remember that water can cross cell membranes to even out the concentration on both sides. This is a process called osmosis. So if we inject something intravenously, such as embalming fluid, we must have a concentration similar to that of blood. And this concentration, the same concentration, has to be of electrolytes in particular. That electrolytic balance is really, really important. And that's part of the reason why for live people, we use, for the IV fluids, we use a base concentration of 0.9% NaCl solution. That's what's used in the hospitals for the base IVs. So we call that an isotonic solution because it keeps the ion concentration is relatively constant. If we have something where we've got too much electrolytes in the solution, then what happens is we get the cells to shrivel. Okay? So if we've got if we have high concentration fluid solution, so it's a high concentration solution, concentrated solution. And here's our cell, and it's got H2O. That water will diffuse through, and when it does that, that diffusion that happens as it osmotically moves through the cell, what happens is we end up with a lower concentration of our solution, but we also, because we got more water there, but what happens is the cell shrivels. Notice that the cell is smaller. So that poses a bit of problem. This is called hypertonicity or hypertonic. If we have it where it's opposite, okay, and we've got something that looks like this, where we have a low concentration of solution. Then what happens is that water from the solution will then move into the cell. And when that happens, now then we have a higher concentration solution, and our cell is bigger, because now then I've got a couple of H2Os in there. Okay? So this poses a bit of a problem, that hypotonic nature. So you have to be pretty careful. If we mess with this in terms of our clientele as funeral directors and embalmers, if we don't focus on this isotonicity right here, this keeping things isotonic, then what will end up occurring is the body will either become hypertonic and will shrivel, requiring us to add hydrating agents, or the body will become hypotonic and will swell, requiring us to use desiccating agents. So you got to be careful when you're working through this embalming. All right, so now then, let's talk a little bit about acidity and basicity. Acids, we think about this, and we kind of understand a little bit about acids. First thing that we think of when we think of acids probably is lemons, right? They taste sour, check. The lemons will react with metals. Did you know that? They will react with metals. So in the case of another example is stomach acid. Stomach acid is HCl. If we have HCl and we react it with some magnesium, we're going to form some magnesium chloride and some hydrogen gas. You can probably look up something similar on YouTube and watch them light the hydrogen gas on fire. It turns also this litmus paper red. Turns blue litmus paper red. Bases, on the other hand, taste bitter. They feel slippery. I mean, they literally feel slippery. And they turn red litmus paper blue. Now, it's harder to think about what are common bases than what are common acids. We don't think about that too much. So in thinking of taste, an example that I would think of would be kale or cabbage, both of which taste relatively bitter. In terms of other things that are bases, they're a common one would be Drano, especially if it uses sodium hydroxide. Okay, that sodium hydroxide is a big deal. That was used back in the old-timey days to make lye soap. Soaps are very slippery, so soaps oftentimes have a little bit of a basic tint to them. Another one that's fairly basic is toothpaste. We don't think much about it, but toothpaste is a little bit basic. We add some flavorants to the toothpaste so that it doesn't taste bitter. So this is an interesting thing. I had a professor one time came back to me and said, which would you rather jump into? You know, we always play the would you rather game at some point in time in life. It was weird when a professor asked me this, but would you rather jump into a vat of acid or would you rather jump into a vat of base? And you know what? The professor said acids, which goes against everything that we've been taught. And then that professor began to explain it. Bases take those proteins that we have that keep our bodies together and it unwinds them, it denatures them. Bases, sorry about that, bases denature protein and in some cases DNA. They unwind your proteins and DNA. So, which would you rather jump into? Acids just burn. Bases destroy your person. Interesting thoughts, right? So, it is really important to maintain a good balance between acids and bases as you are embalming a body. So you got to understand some things about acids and bases. One is there's something called a neutralization reaction. If I take an acid and I react it with a base, I'm going to produce a salt and I'm going to produce water every time. So if it takes hydrochloric acid, I can react it with sodium hydroxide. That produces sodium chloride and water. So the salt is usually a metal and a nonmetal. And we see this neutralization reaction occur. Another neat little reaction here that you can do would involve, let me think here. You know that Pepto-Bismol? If you don't feel very good and you need to deal with some upset stomach. If I recall right, it uses a little bit of barium hydroxide. So that barium hydroxide will react with HCl as your stomach acid and produce barium chloride plus H2O. But this isn't balanced, okay? So you got to use two of these because here's barium and here's two chlorides, so you need that to get here. And then you got two OHs, and now then two H's, and that gets you two H2Os. So this is a nice way to begin to work as an antacid. That's an anti-acid. Which, of course, reminds me of the old joke. What do you do when a chemist dies? You bury him. Moving on. Let's get through some definitions. An acid can be loosely defined as something that produces hydrogen ions in water. So let's think about this. HCl, we've already defined and called an acid. HCl in water, when we dissolve it in H2O, will produce H plus Cl minus. So it kind of produces the hydrogen ions in water. Interestingly, what it really does is it divides up the HCl there. It divides those things up. And then what we find is this H plus goes on and reacts with the H2O to form H3O plus, which is called a hydronium ion. Because an H plus isn't really formed in water, it is actually bound to a water itself. A base is something that produces hydroxide ions in water. So if we go back to the standard sodium hydroxide, if we take sodium hydroxide and we dissolve it in H2O, then what happens is you get Na plus, which is perfectly content just existing like that, plus OH minus. Notice the base formed OH minus in water, the acid formed H plus in water. So, loosely speaking, this works. Many metal oxides also form hydroxides when reacted with water. So calcium oxide will produce calcium hydroxide. Lye soap is made from ashes. Hold on. Where do we find this? Where are ashes found? For our business, it is found in the crematorium, isn't it? So you must clean the crematorium well. Otherwise, it begins to degrade the metals if you're not careful. For the neutralization reaction, really and truly, what we actually have is the reaction of H plus to form OH, of H plus and OH minus to form H2O. So let's look at this. If I take the reactions above, that NaCl and that HCl, we're looking to see if can we get that reaction that I'm showing here. NaOH ends up falling apart to produce Na plus and OH minus, right? HCl falls apart to form H plus. Let me rearrange it real quick. Okay, ready? Just deal with me. Cl minus plus H plus. If I take these two reactions and I put them together, what do I got? Bibbidi, bobbidi, boo. So I want you to see something. Really, the sodium chloride stays dissolved in water, right? I've dissolved all this stuff in H2O. This is water that's dissolving it all, okay? Lots of H2O around. It's a great aqueous solution. So NaCl, does it actually come back together to form salt crystals? No. It stays like this. So these are actually called spectator ions. They don't do the reacting. So what really is doing the reacting is what? OH minus and H plus reacts together in this water to form H2O. Do you see that above? Isn't that just fancy? So, as we're looking through some of this, recognizing acids and bases fairly straightforward. Acids, typically, you have an H at the beginning. So you have an HCl, H2SO4, H2CO3, which is known as carbonic acid, which is really important for our Cokes. The generic Cokes, because we're in Tennessee and that's the way it works. What else? How about HNO3? That's an acid. How about HNO2? That's an acid. How about HI? Well, hello to you too. That's an acid, right? Bases will tend to have an OH with a metal. So you get the NaOH, you get the magnesium hydroxide. That's how you would name this. Magnesium and then the hydroxide ion. Please memorize the hydroxide ion. It's really important. What are some other things? Well, as I showed you before, barium hydroxide, right? Some other type things. You can just kind of go on down the list. How about KOH? Potassium hydroxide. That is especially wonderful. And then there's this interesting one. Ammonia. Ammonia is a base because it reacts with water and forms ammonium hydroxide. That ammonium hydroxide is NH4OH. See it right there? So ammonia reacts with water to do this. It is a hydrolysis reaction. That means it breaks water apart to form something else. Hydro as in water, lysis as in to cleave. So, ammonia will react with water to form a base. So now then that makes a little bit more sense. Where will we use ammonia? Oftentimes you use ammonia as a disinfectant, right? As a cleaner. So, how can we use these things? How can we make sure that we use them well and appropriately? Well, another great question. We've got to be able to measure our acidity. So we use something called a pH scale. This thing you need to memorize. Memorize, okay? Please, memorize. See, here's some eyes. Okay? And here's okay, memorize, okay. So we have something called a pH scale. The pH scale ranges from 0 to 14. A pH of 7 is absolutely completely neutral. A pH less than 7 is acidic, and a pH more than 7 is basic. Blood, its pH is equal to right around 7.4. So it's a little bit basic. Kind of contrary to what you might think. So, in looking at pH, it actually measures the number of the H plus ions, these hydrogen ions. Lots of hydrogen ions means more acidic, lower pH. Less means less acidic and a higher pH. So pH, the actual formula for pH is this. pH is equal to negative log, that's from your calculator, concentration of H plus, or H3O plus, whichever way. So this right here actually means this is a concentration of H plus. So as that concentration gets higher, pH goes down. So recall this. As H plus increases, pH decreases. Okay? That means as you have more H plus ions, it becomes more acidic. And that makes sense, I think. So let's think through some of this stuff. What about stomach juices? Because juices just sounds wonky, doesn't it? Well, I already said stomach acid a while ago. That's a nice little acidic kind of thing. Ammonia? I already said it's basic. So it's a base. What about water? Ooh. Well, let's skip that one. How about lemon juice? Lemon juice is acidic. What about Drano? Basic. What about, so we got water, we got household cleaners. Well, Drano is a cleaner. Ammonia is a cleaner. So I guess maybe we'll call them basic. But what about vinegar? White vinegar is an excellent cleaner. So it can also be acidic. Huh. What about water? Pure water is absolutely and completely neutral. Look at that. So, concentration determines pH. Remember, I said that pH is equal to the negative log of this stuff, right? That stuff, that concentration, is a molarity. Do you see this? It's a molarity. So I am not going to make you memorize molarity and how to calculate pH and all that kind of stuff. What I'm more interested in is, can you actually look at something, look at a pH reading and know what that means? Okay? So, for instance, in a neutral solution, well, this is a lot of stuff. So we know that the concentration of H plus times the concentration of OH minus is equal to 10 to the negative 14th. Okay. In a neutral solution, that means H plus has to equal 10 to the negative 7th, and that's also equal to OH minus, okay? So we know we got to pay attention to this, got to pay attention to this, and then that yields this thing right here. The negative log of the concentration in a neutral solution gives us a pH of 7. If we have a pH of 2, then that means the concentration of H plus is negative 10 to the negative 2. So we can do some interesting things. If we have a concentration, you can do a lot of estimations here. If I have 10 to the negative 7th, then that means, so this is the concentration of H plus. What's the pH? It's going to be on the order of 7. If it's 10 to the negative 8th, the pH is 8. What if it's 10 to the negative 12th? pH is 12. What if it's 10 to the negative 3? Then the pH is 3. What if it's 10 to the negative 5? Then the pH is 5. You see this? So what you can do is you can start using this thing right here as a way to kind of estimate your pHs without ever doing math. Okay? So 10 to the negative 1 would be a pH of 1, negative 2, pH 2, negative 3, pH 3, and so forth. You can find the pattern there. Know how to use the pattern, know what the pHs mean. There's another interesting thing. We've addressed this once, but I want to address it again. You have redox reactions or oxidation reduction reactions. oxidation first. Oxidation is loss of electrons. Reduction is gain of electrons. Remember I said, being from Texas, I like oil rig. Oxidation is loss. Reduction is gain. Okay? That works pretty well for my brain. You need to figure out what works well for your brain. So oxidation is a really common type of chemical reaction. And anytime oxidation occurs, you're typically going to have a reduction occur too. That's why we typically call these things, more often than not, redox reactions for reduction oxidation. Okay? So these redox reactions, one example is when you take two elements and you react them together. So if I take sodium and react it with chlorine, sodium has a 0 charge and chlorine has a 0 charge because they're both elemental, right? But whenever we react them together, and you can look at this reaction on YouTube as a sodium reacting with chlorine gas, we get an Na plus and a Cl minus. So when we connect the chlorines together, we see it goes negative, and when we connect the sodiums together, we see it goes positive. So I want you to recall this. If you go from 0 to positive, then that means you're plus 1 electron on the positive end. So that means going from the reactant to the product, this is lost. When you go from 0 and you react it and you become negative, that negative has to come from somewhere. That negative has to come from something else, right? So that means when you go from 0 to negative, you have to gain an electron, which means chlorine is being reduced, or we have a reduction occurring, and with sodium we're being oxidized. We can do the same thing with H2O2 going to H2O. We have a 0 here and a 0 here. We get a plus 1 for H and we get a 2 minus for oxygen. Oxidation occurs where? Well, let's see. Oxidation happens when you go from positive to negative. So from here to there. Well, hold on. That's not the right way. Oxidation occurs when you are losing an electron. So that happened right here. Reduction happens here. So, what about something that's a little bit more interesting? Let's look at this. This is not an oxidation reduction reaction. It is not a redox reaction. Why? All right, let's walk through this. Nitrate, this NO3 right here, is a -1. And because we have 2 of them, that means lead is a +2. Okay? Chlorine is a -1. Hydrogen is +1. So if we come over to the other side, we find that hydrogen over here is +1. And what about this nitrate? What is it? It's a negative one, okay? So let's do a quick check. Let's check nitrate right here. Did the charge change? No, it did not. Okay, so we're not going to mess with that. What about this lead chloride on the other side? Well, chlorine is a negative charge, right? And if I have two negative charges here, then lead has to be 2 plus, correct? So let's check. Chlorine, negative to chlorine, negative. Nothing there. What about lead? Lead positive 2 to lead positive 2. Nothing new. Do you see how it is not a redox reaction? Those oxidation numbers didn't change. Even this hydrogen right here didn't change. So we do not have an oxidation reduction reaction. When you see those charges change, then you tend to have an oxidation reduction reaction. Loss of electrons is oxidation. So some people like the lion version. Leo goes grr. Loss of electrons is oxidation, Leo. And grr is gain of electrons is reduction. How can you tell if something loses electrons? Look at the charge. If it becomes positive, how can you tell? It becomes, I'm going to say it this way, more positive. For instance, you can do something like this, where you have Mn2 plus that becomes Mn4 plus. It didn't just become positive, it became more positive. As a result, we have lost electrons. Therefore, it is oxidized. If it gains electrons, then it becomes reduced. All right. Hopefully you had fun with this nice little lecture on acids and bases and a reminder on the oxidation and reduction. Don't stress too much. Do not stress too much. I can't repeat this enough. Do not stress too much about trying to calculate the acid bases, the pHs of things. I want you to focus on being able to determine if something is acidic, neutral, or basic. That's what's a little bit more important. We'll also have a couple of acid-base reactions that we probably ought to pay attention to as well.